Welcome to the second part of the Chapter 2 topic for the Precalculus course. Now, we are now at Chapter 2, Polynomial in Power and Rational Functions. Last time we talked about the basic linear and quadratic function and modeling, and we have expanded upon it in class, and we have now practiced a little bit on how to apply both concepts into solving problems and applying it in real-life situations. Now, with this topic, with the second part for the polynomial power and rational functions chapter, this time we're going to tackle power functions with modeling. So with the power function, we're going to expand more on the characteristics and the descriptions and analysis of the power functions that we are going to encounter in future calculus subjects and even calculus in general in the future. So, let's talk about the power function. For the power function, last time we talked about the 12 basic functions, and actually some of them are technically power functions already, and we didn't really realize it at first, but we are already tackling power functions since the beginning of algebra. The first one is the basic y is equal to x, which is the line equation with the power of 1. The y is equal to x squared, which is the parabolic equation or the quadratic function, power of 2, and y is equal to x cubed, the cubing function or the cubic function. So we have a power of 3. And also we have this, which is the 1 over x, which is an inverse function. And this technically has a power of -1. That's the reason why the x is at the denominator. Let's expand further. Let's define it. So defining a power function, as we usually do in algebra and in precalculus, we always have a notation. And in this case, the function of x is equal to k multiplied by x raised to a. Now let's talk about the different components of this notation or this function. So for the k, we know this is the constant. Sometimes in other parts of precalculus or even in calculus, we refer to this as the constant of variation. In algebra, it was discussed that we have two kinds of variations. We will tackle that in a bit. So that's one thing to remember. And the other one is the constant of proportion. If you encounter both of these terms, they basically refer to the same thing, which is the constant multiplied to the variable raised to a power of a. Now, moving on to a, this is the power. So any number for a will basically tell you what kind of power your variable has. So if, for example, for a quadratic function, we have a power of 2, which is something that we know already. Let's move on. So in your endeavor in math, since geometry or even in physics and other fields, we are actually manipulating, or we are utilizing a lot of power functions in our computation, in our problem solving. And this is normal because a lot of the applications of power functions are in real life actually. Like for example, in geometry we remember the circumference. The circumference is the total length, the perimeter, if you will, of a circle. So the total length around the circle. And we know that this formula is equal to c is equal to 2 pi r. And looking at it closely, it doesn't look like much yet, but actually this is a linear function. This is a linear equation, with the 2 pi being our constant of variation and the r being the independent variable in this equation. So in this regard, we can now isolate the a and the k for us, and we have an a of 1 because we know that the power of r is 1 and k is equal to 2 pi. So 2 pi is the constant in this case. Next is the area of the circle. This is something we're already familiar with. So in turn, this is a quadratic function with a as a function of r. And moving on, we're going to have the a or the power. We have 2, so this is the power of 2, and our constant of proportionality is pi. Easy stuff. But for something more advanced, if you already encountered this in physics, we have something called the gravitational force. This is the force exerted by two mass in space, and the closer they are together, the more powerful the force between them are. So it's F is equal to K over D squared. Now, if you notice that the variable, or the independent variable in this case, is D squared, which is in the denominator, and it's as a power of 2. In return, our A, or our power, is a negative 2 now. Only because technically D has a power of negative 2 if we're going to put it in the numerator. And for our constant, we have the K, which is still K. Next, we have the Boyle's law. And following this formula of V is equal to K over P, same goes. So instead of 1, we have negative 1 as our power for this variable P, and the K is the same as the constant. Dividing them, and we are going to notice something. For the area of the circumference and the area of the circle, we have a completely direct variation of the changes between the R and the C for circumference, and the changes of R affecting A. So if you remember from your algebra, this is something that we call a direct variation. If your power, or if the power in your function or in your model is a positive number, it is a direct variation. In the case of the other two below, the gravitational force and the Boyle's law equation, we notice that the variables are in the denominator, and they have their own powers, and since they are negative, we call them inverse variation, which is something that we already tackled in algebra. Let's go for an example. State the power and constant of variation of the function, graph it, and analyze it. We have two equations. F of x is equal to cube roots of x, and g of x is equal to 1 over x squared. Okay, let's focus on x. Let's focus on cube roots of x first. If we look at this, it's a radical, but it's a radical with I would say power of 3 in that case, or it's a 1/3 power of x. Translating that further, or rewriting the equation to a different notation, this is the same as x raised to 1 over 3. Okay, so if we further dissect this equation, we're going to have 1 times x raised to 1/3, which is true because we know that there is technically a constant multiplied to the x raised to 1 over 3, which is 1, of course. And we have the k and the a is equal to 1/3. We know that the k is the constant, so that's 1. And the a is equal to 1/3, which is the power. So it's easy to identify. But now let's try to analyze the whole thing. If you use your graphing tool, or you use any graphing device that you can have, you're gonna end up with this graph, or this curve. You're gonna notice right away that this vaguely follows the cubing function shape-ish, if you will, because we're going to talk later. It's going to be an odd function. So that's a prediction. First, let's talk about the domain. Looking at the graph by itself, we can already see that from negative x to positive x, anywhere in there, we know that there are no asymptotes because our independent variable is not within the denominator of your function, which means that there's no way for you to have there's no way yet. Well, there is. There's a way for an asymptote to form, but in this case, there's none. So if you propagate your graph from the left to the right, you're going to have a domain of negative infinity or positive infinity, which means all real numbers. For the range, same goes. So if you travel from negative y to positive y, you're going to see the same thing. Your graph will propagate forever from negative infinity all the way up forever to positive infinity. Okay, we know that. So in terms of x, if we look at the general slope of the whole curve, we can see that the slope of x is increasing. So there's that pattern over there, and it's an odd function. Mainly because if we look at the origin, we can see that the graph, or some parts of the graph, are actually mirrored in the x-axis. So if you try to compare the quadrant 1 to quadrant 3, you can see that they're actually mirror copies of each other. Looking this further, we know that there are no local extrema because we know for cubing function or any derivatives of it or any variations of it, we know that there are, well, in this case at least, there won't be a local extrema because we can see over there that it doesn't really have that peak or the dip. It doesn't have a point where the graph will change from decreasing to increasing and from increasing to decreasing. So, and of course, no asymptotes because we don't see any parts in the graph that prevents the curve to be continuous, and at the same time we know that we can accept any value for x and y, so no asymptotes for this one. Let's move on. Okay, so let's see 1 over x squared. Moving further, we know that this is going to be the same as x raised to negative 2. Moving further, we know that this is also 1 times x raised to negative 2 with k equal to 1 as our constant of proportionality or constant of variation, and our a will be negative 2 because the variable is in the denominator. So as a clue already, since our x, our variable, is in the denominator, we can expect already that there's going to be at least one asymptote for this one. So let's try to graph it. If we graph it, we're going to end up with something like this, and you will see that already I can see that there are 2 asymptotes that we have. It's at x is equal to 0 and y is equal to 0. So basically our x and y axes are the asymptotes for this one. Okay, let's move on. And to the domain, if you try to propagate your graph from the negative infinity side all the way to the positive infinity side, you're going to notice that at least for x, 0 is forbidden. Your graph will never ever touch 0 because, true enough, if your x is equal to 0, your y becomes an infinite number or an undefined number, which is a no-no. So our domain will be like this, from negative infinity to 0 in union of the other, which is 0 to positive infinity. So basically any real number except for 0, for x at least. For the range, we have this. Since we know that our graph never reaches or never touches the negative part of y, we can safely assume that the range starts from 0. Note that the open parenthesis over there indicating that the value should never be at 0, but approaching 0, and it goes all the way to positive infinity. Now let's go check the increasing side. So if you can see here, from the left side, we can see that there's a general increasing slope from negative infinity to 0. And again, we're not considering 0 as a number. That's why we have a close parenthesis for that one. For the other side, for 0 to positive infinity, our general slope is decreasing, as we can see. And for this one, it's an even function because we have a 2 there. So if you try to replace the x with a negative x, you're still going to end up with the same function. So it's an even function. We have no local extrema, only because there are no veritable dips or peaks in the graph. We can see that. And of course, our asymptotes will be from, well, we have y is equal to 0 and x is equal to 0. So that's what we got. Let's move on. Now, in power functions, the most basic that we can find are monomial functions. As mentioned in discussion, monomial functions are basically polynomials with one term only. So there's a single term in your polynomial. So there's only one there. And it follows this notation, which is basically very similar to the power function notation with a little bit of tweak there. Instead of a, we use n. And this is a single term polynomial, and we know that if you have just this, any number that you put for k and n, if your x is equal to 0, your y will always be 0. So a key characteristic for this, for all monomial functions, will pass through the origin at 0, 0. Let me show you something. Okay, look at this graph. So I basically set the value for the highest y as 1 and the highest value for x is equal to 1. So basically I'm setting up a boundary of if x is equal to 1, y is equal to 1. So if you use the parent functions for each power of 1 to 6, you can see here that the f1 of x is equal to x is a linear function. We know this. So if you look at it closely, it's of course a straight line. with a quantifiable steady slope. And if you notice, as you go along with the power, you can see that it actually moves to the right and down a little bit. It forms this sort of concavity in itself, and it's actually a feature of power functions when you look at it. So it's going to give you more of a curve when you try to graph it, the more power you give to the function. So at 1, at x is equal to 1 and y is equal to 1, the monomial pairing function all follow a similar increasing slope. We know this. If you project a line, which is probably just the line for y is equal to x, you will know that all of these powers from 1 to 6, or even any number actually, any positive number, will give you an increasing slope, at least in the case of at x is equal to 1 and y is equal to 1. And that's a key characteristic for a monomial function. So there is basically a uniformity when your x is equal to 1. So you're going to end up always with y is equal to 1, granted that it's a parent function. When your a is different, it's going to be a completely different graph. Let's move on. So one of the first things that we do when you have power functions, of course, is to model it. We discussed this in class. We know how to use a graphing tool, how to get the line of best fit or curve of best fit when it comes to the graph. In the case of modeling, it's the same thing. You just have to be careful with your modeling, because if you choose exponential or quadratic, it's only going to follow a quadratic path. But the nice thing about the power function, at least in your graphing tool, you will notice that it will adjust to the points better than, let's say, if you just chose an exponential or say a quadratic function or a quadratic regression. Let's see. Let's get an example. So we have this table. You use the table to obtain a power function, so it's specific, for orbital period as a function of average distance from the sun. Use the model to predict the orbital period for Neptune, which is 4497 gigameters from the sun on average. So that's far away Neptune is from the sun. So we have these table, these values, and we can now input them into our trusty graphing calculator. In my case, I use a TI Inspire CAS2, and you got to be careful on this one. So let's try to remember or let's try to recall something from the problem. It says there, power function modeling for orbital period as a function of average distance, which means that orbital period will be our dependent variable, and our independent variable will be the distance from the sun. So this will be the pointer, or this will be our hint. Where are we going to put the different axes when we graph it? So if you input this into your calculator, you're going to end up with a graph that looks a little bit like this. Okay, so at first glance, it kind of looks like a quadratic function. It kind of looks like it. It's really close to one. If you look at the equation there, it's actually raised to 1.5, which is really close to 2, but not quite the same. So there's a curve right there, seemingly emulating a quadratic function. But we gotta know what's the accurate model for this one. So if you try to use the regression tool, the analyze tool from your calculator, you're going to use the power function regression option over there, and it's going to give you this model. So with this model, we can see it's safe to round it up a little bit. Sometimes it is, sometimes it's not. So in this case, I'm going to allow it. So in this case, I'm going to rewrite the equation as T of A stands for period, and A stands for the average distance, equal to 0.2 A raised to 1.5. So that's your power function. Technically it is, because 1.5 is a power function, 3/2. So let's answer the question. We need to find the period of days for Neptune, which is 4497 gigameters away from the sun. It's a long distance. It's a far away. So let's try to put in the value. So when your A is equal to 4497 gigameters. You plug that into your model. So T of A is equal to 0.2 times 4497 raised to 3 over 2, or 1.5. And you're going to end up with T of A is equal to 60,313 days. So good. So we got to approximate, or we got to estimate the value, or the period in which Neptune revolves around the sun, which is 60,000 days. So that's how we use a power function for modeling, and we're gonna have more of this in the future, in the coming days. We get to practice applications of power function, which is exciting stuff. So that's it for now. That's the briefer for this new part of the chapter, and I'll see you again in the next video.